Remember that a distribution tells you how likely is each of the possible values of a random variable. Previously, we looked at the normal distribution for continuous random variables. If a variable is normally distributed, we can use the normal distribution table to find out how often any particular value of the random variable will occur. For example, suppose we know that the mean and standard deviation of the heights of students at the university, and we think that the heights are normally distributed. We could then use the normal distribution to find out how many students are under 5 feet tall, or over 6 feet tall, or who are between 5 and 6 feet tall. Today we're going to add a bit more complexity to this notion of a distribution in order to answer the question, how likely is it that my sample statistic is close to the population parameter? Recall that a population is all of the possible subjects, and a sample is the group of subjects for whom we have data. A parameter is a numerical summary of the population, and a statistic is a numerical summary of the sample. We're interested in populations, but we only actually know about samples, so we use the sample statistic to estimate the population parameters. For example, if we wanted to find out the average height of students at the university, a population, we might take a sample of 100 students, that's the sample, measure their height, now we have data, and compute the sample mean, a statistic. We then use that sample mean of just those 100 students as an estimate of the population mean, the average height of all students at the university. Because it's calculated with just a small number of students, the sample mean won't be exactly the same as the population mean. If we repeated the study with a new sample, we'd get a slightly different sample mean. But it will hopefully be close. How close? That's the question we're going to answer today. Before we get there, though, let's refresh some concepts. Remember that a random variable is a number that we attach to some outcome of a random phenomenon. For example, roll a die and count the number of pips on top. For a 6-sided die, there are 6 possible outcomes, and we attach a number to each one, the same number as the number of pips on the face of each die. Or select a random student from Regis College and measure their height. Here, there are about 2,000 possible outcomes, each of the students in the college, and we use their height as the number for the random variable. Now, these random variables can correspond to compound outcomes as well. Instead of just rolling one die, we might roll 2 dice and add up all the pips. Or we might roll 2 dice and draw a card, adding the number of pips to the number on the card. Let's think about the compound event of a series of coin flips. Say you decide to flip a coin 5 times and find the proportion of heads. What are the possible values of the random variable? Well, the proportion could be 0, 1/5, 2/5, 3/5, 4/5, or 1. We could then find out the probability of the random variable being any of these values. Here's what they happen to be. So if you and a bunch of friends each flipped a coin 5 times and found the proportion of heads, some of you would get a 5th, others would get 2/5, still others would get 3/5, and so forth. But most likely, more of you would get 2/5 or 3/5 than any of the other values, since those are the most likely. Here, each individual coin flip has its own probability distribution. You have for each coin flip either a 50% chance of getting a head or a 50% chance of getting a tail. But the combination of 5 coin flips has a different distribution from the distribution of each of the individual coin flips. What if instead of flipping a coin 5 times, you instead flip the coin 10 times each? Then what are the possible values for the proportion of heads? Well, you could have 0, 1/10, 2/10, and so forth up to 9/10, or 1. This is a different random variable with different possible values, each of which has some probability of happening. Here's what those probabilities look like. So if you and a bunch of friends were to perform the experiment of flipping a coin 10 times, some of you would find a proportion of heads as, say, 3/10, and others 7/10, but most would probably find between 4 and 6/10. Here, each individual coin flip still has the same distribution as before, 50% for heads, 50% for tails. But the combination of 10 coin flips has a different distribution from the distribution of 5 coin flips. Notice how the second distribution isn't quite as spread out. More of the probability is located near the center and less of it near the edges. Now think about finding the height of a student at the university. There's some distribution for the height of a student. Say it looks something like this. And there's some probability that a student will be, say, 5 feet or 5 feet 1, some probability that they're 5 feet 2, and so on. But when we collect data for a sample, we usually measure more than just one student. We measure a bunch of students. We can think of the sample mean as a random variable that corresponds with a compound random phenomenon. The random process not of selecting a single student and measuring their height, but the process of selecting some number, say 100 students, measuring each of their heights and finding the average. Just as with the coin flips, the mean height of a sample of 100 students will have a different distribution than the distribution for the height of a single student. The distribution of the mean is called a sampling distribution. This is the set of values that a sample statistic can take and the probability of observing each of those values. It's the distribution that would result if you and a bunch of your friends each took a different sample of the same size and computed the statistic, such as the mean. The sampling distribution shows how the sample statistic would vary if several similar studies were conducted. Now, we started this session by remembering that we're interested in populations, but we only have data for samples. So we use statistics to estimate population parameters. This leads to the question, how good are these estimates? The sampling distribution lets us answer this question. The sampling distribution tells us how likely it would be to observe some particular value of the sample mean, or put another way, the sampling distribution tells us how likely it is for the sample mean to be close to or far away from the population mean. We've talked about several different types of distributions, and it might be a little tricky keeping them separate. We have the population distribution. This is how many of each of the possible values there are of x, the random variable, such as student height, as they're seen in the entire population. Then we have the data distribution. These are how many of each of the possible values of x are seen in one sample. What are the student heights in this sample of 100 students? The data distribution will approximate the population distribution with a large enough sample size. We looked at this in the first computer lab in the last session. Finally, we have the sampling distribution. This is how often you would see different values of the mean of x, or some other statistic, for samples of a given size. We actually looked at sampling distributions in the fourth computer lab in last session. Now, we're interested in how close a sample statistic is to the population parameter. The sampling distribution tells us how likely each possible value of the sample statistic is. It would be interesting to know if the possible values of the sample statistic are really spread out or if they're quite similar. We used the standard deviation before as a summary of how spread out the values were, and we can talk about the standard deviation of the sample means from many similar studies. The standard deviation of the sampling distribution is so useful and important that we give it a special name. It's called the standard error. The standard error is the standard deviation of a sampling distribution, and it indicates how much variation there would be in a statistic between many similar studies. So what shape does the sampling distribution have? In the fourth activity of the computer lab, you took a bunch of samples from several different populations and looked at the sampling distribution for the sample mean. You notice that no matter what population you started with, if the sample size was large enough, the sample mean tended to have a symmetric bell-shaped distribution. This result is called the central limit theorem. The central limit theorem says that for sufficiently large random samples, the sample mean approximately follows a normal distribution, no matter what the population distribution. It's the central limit theorem that allows us to make inferences about populations, even though we don't know what the population distribution looks like. It could be symmetric or very skewed. We know that for a large enough sample, the mean will follow a normal distribution. So if our sample size is large enough, we know that the sampling distribution for the sample mean will have an approximately normal distribution. Recall that to characterize a normal distribution, we need to know the mean and the standard deviation. Since we're talking about sampling distributions, we could say the mean and the standard error. So what do we use for the mean and the standard error? Well, first we can talk about the sampling distribution for a sample mean. For a random sample of size n from a population with some mean mu and standard deviation sigma, the sampling distribution of the sample mean has center or mean mu, the same as the population mean, and it has standard error or spread of sigma divided by the square root of n. So the sampling distribution for the mean has the same mean as the population mean, but it has less variability. Instead of having a standard deviation sigma like in the population, the standard error for the sampling distribution is sigma divided by the square root of n. Let's look at an example. For the population of farm workers in New Zealand, suppose that weekly income has a distribution that is skewed to the right with a mean of $500 and a standard deviation of $160. A researcher unaware of these values plans to randomly sample 100 farmers and use the sample mean annual income to estimate the population mean mu. What's the standard error of this estimate? Well, we take the standard deviation of the population, 160, and we divide by the square root of n, which is the square root of 100, that's 10. So 160 divided by 10 is 16. The standard error, the variability in the researcher's sample mean, is $16. So in what range will 95% of the sample means of studies like this one fall? For a normal distribution, we know that 95% of the values will fall within 2 standard deviations of the mean. 2 standard deviations of the sampling distribution is $32, so 95% of sample means from studies like this one will fall within $32 of $500, which is the population mean, and the mean of the sampling distribution. So that is to say, 95% of the sample means from studies like this one will be between $468 and $532. In what range will 99% of the sample means of studies like this one fall? Well, from a normal distribution, 99% of the values will fall within about 3 standard deviations of the mean. The sampling distribution has a standard error of $16, so 3 standard errors would be $48. So 99% of sample means from studies like this one will fall within $48 of $500, the mean. That is to say, between $452 and $548. In addition to talking about the sampling distribution of a mean, we can also talk about the sampling distribution of a proportion. For a random sample of size n from a population with some proportion p, the sampling distribution for a proportion has mean p and standard error square root of p times 1 minus p divided by n. So whatever the proportion is in the population, p, we know that the sampling distribution of our sample proportion is also going to have mean p. But not all of the samples will have exactly the same proportion as the population proportion. So there's some variability around that. And that variability is characterized by the standard error, the square root of p times 1 minus p divided by n. Let's look at an example. In the Californian gubernatorial election of 2006, Republican incumbent Arnold Schwarzenegger was running against Democratic challenger Phil Angelides. In the actual election, Schwarzenegger won with 55.9% of the vote. Consider an exit poll of 2,705 people. What are the mean and standard error of this sampling distribution? So we know that the population proportion is 55.9%, but we don't yet know the results of the election. We only have data for 2,705 people who answered a poll as they were leaving their polling place. And we know that the sample proportion that we calculate from this exit poll is not going to be exactly the same as the election proportion. It's going to be close, but it's not going to be exactly the same. It's going to come from some sampling distribution that has a normal distribution with a certain mean and standard error. So the mean for the sampling distribution is going to be the same as the population proportion, so 0.559. And the standard error is going to be the square root of p times 1 minus p divided by n. So that means the square root of 0.559 times 1 minus 0.559 divided by the sample size 2,705. That gives us 0.01. So 95% of similar exit polls would be within 2% of the election proportion. You can imagine that news stations all over California might conduct exit polls like this. Maybe some in San Francisco, some in Los Angeles, and ignoring any regional variation in how people cast their vote, about 95% of those exit polls would be within 2% of the actual election results.